Hi, everyone. I'm Marty Fulton with SNIA again. We're back live, truly live. We've been live all afternoon with Scott Shadley, the co-chair of the SNIA Computational Storage Technical Work Group, and David McIntyre, a contributor to the SNIA Compute Memory and Storage Initiative, who both presented on computational storage and are going to answer some questions that came out of the previous sessions. So I will turn it over to with an initial question that came out of the session we just concluded with David, someone had asked about how you secure shared data, David.
So securing sharing data, I guess, it depends on how you look at it. If it has to do with drives that are working in a peer-to-peer standpoint, then there's a way to provide some of those security mechanisms that I talked about earlier, where you can have a need-to-know movement of that data. So as an example of, I mentioned healthcare privacy. If there's a particular group of patients and that data is sitting on one drive, and you would need to check on security policy before you're actually moving that data over to the other drive, to perhaps because you need to provision the computing power across drives just to load balance. So that is one mechanism to protect that type of data for sharing. Scott, how would you look at that? How would you view that same question?
Yeah, I agree that there's just lots of differences that need to be looked into, but yet there's a lot of similarities at the same time. So there's not a huge scary thing out there when it comes to security around this stuff. It just needs to be properly looked at, managed, and I think a good example of that is, as part of the computational storage working group, we're partnering with the security working group that you're a part of as well, to make sure that whatever we do is at least reviewed by the people that are smarter than me in security, so that what I do doesn't create more problems for them or for the users or customers. So. Yeah.
And in fact, this is a good example because we would probably need to better define the context of the question, but that's what this group is about. It's about getting ahead of it before it happens and looking at all what does this type of question actually mean, and what are the scenarios and applications that we need to address as a security or as a community. So not a very specific answer, but one that shows that we're willing to address that type of situation.
Absolutely.
So I have a question for both of you that came in, that how easy is it to deploy computational storage solutions?
So I'll go ahead and jump in there to start, and let David jump in after that. Yeah. But, it comes down to today, what type and how they're provided to the user, right? One of the key things that the computational storage working group is driving towards is creating a framework that all the devices will coherently address or work with. So no matter what they do as far as the processing engine part of it, they'll interact with the user in the same way. And that's a very key part of helping make them easier to deploy. There are some that do require some unique changes to the platform today, others that don't require much change at all. So I think from an overall point of view, it's moving forward with what we're doing in SNIA is of huge support. And that's one reason why Samsung, myself, and a few others were founding members of the working group. Is like, we knew this technology is needed. We knew it's not coming to market today, right? That was, of course, 2018. It is today. All right, we're ready to deploy it today, but we need guidelines to help make it that much easier to work with.
Yeah, it's a new world with computational storage, where before hardware vendors would develop a solid-state drive, and it would just plug in through some NVMe standardization and just work. Now, because we're basically a part of the processing complex, because we're doing in-situ processing down at the drive level, as Scott was talking about having a framework put in place, the implementation of that framework is in not just the hardware itself, but also defining the proper APIs that need to be developed so that the users can directly access those computational storage drives with not only the hardware features that they need to access for speeds and feeds, but also from an application standpoint, as well as a security standpoint. So we're basically we have to provide a multi-layer level solution at a system level, where before we just needed to have the fastest and highest capacity drives out there.
So Scott, you had spoken about really tying computational storage to Linux, and there is a specific question about rewriting applications or the kernel for computational storage.
Yeah, and that's definitely a big trick, and especially for me as a hardware vendor, I'm like, rewrite an application, who cares, right? I'm a hardware guy. But from a user, especially from those that are using SODA and Linux and other, the guys that are actually deploying the software on these devices, it's key. You think of it as like your little baby. If you build a Lego set and someone decides to come and rewrite the way you way you built your Legos, you don't like that as a kid. I don't like it anymore as a user of a software platform, that the code that I've written or the code that I've learned to deploy through my dummies for books or whatever has to be changed or modified in some way to actually work in a new device. A new device needs to adapt to what I've already done and make what I've already done better with as little change as possible. And that's really kind of the focus of what you have to do from that point of view, from my perspective.
Mm-hmm. There are a couple of models that have been talked about for computational storage. One is to just do functional offload from the host, where you're just doing just that. You have an FPGA or an ASIC within the computational storage device, offloading the host processor and running specific functions. It could be on database queries. The other architecture, of course, is running a whole database on the drive itself with little to no interaction with the host. And if you're running a Linux-based application, there's actually some, at least for the functional offload drive, there's things like eBPF, which allow you to tunnel into the FPGA without actually disturbing the Linux kernel itself. And so those sorts of implementations are we're talking more about those more and more with our system level customers. But I think it comes down to how much do you want to put in the drive, if it's just the offload, or actually the ability to run the whole database or whole application itself on the drive. And with cloud to edge, that becomes more and more opportunistic.
Absolutely, and I would agree that there are some things, of course, they can't fit, for example, in the type of processing that's available on the devices. And
Yep.
Berkeley packet filters are great. It's a perfect implementation for something that uses bytecode and things like that. So the FPGA architectures that are out there today are great for that type of deployment. When you get into like the on-drive Linux that I was speaking to, since it's a replication of the host user environment, it's a copy paste, and that's one thing I think is very valuable. That can be very valuable for some people as well. Not trying to distract or say that either one's better than the other. That's why they both exist today.
So we have a great blog that'll be coming out on SNIA.org about eBPF probably next week. So more details on that. We have time for one final question, gentlemen, and I think it applies to both of your talks. There was a question about how is a processing device that's not in the host operating system or CPU or still secure? How can it remain secure?
I'll let the security expert start that one.
When in the presentation I just gave, I basically said, look, that's another function or variable that needs to be included in the equation. And I showed a number of methods to provide defense around that compute element. Like if there's an SoC, a system on chip ARM processor within the FPGA itself, you can actually build a fencing around that particular region of the FPGA. If it's an ASIC offload that perhaps has an ARM or a RISC-V in it, you can basically, through root of trust, ensure that not only that component, but others within the drive itself are meeting the proper standardization and security protections.
Yeah, and there's also partnerships that can be had with these types of things. Like I know of a company that my organization is working with that has a secure root of trust Linux that can be deployed on what we would classify embedded devices, and the the CSDs are classifying that space as an embedded device and can actually be that root of trust carryover, if you will.
Okay, I think our time is up, but I encourage everyone that's on our presentation to move over to the next presentation by Eric Hibbert of SNIA, which will expand the security parameter, and we'll talk more broadly about security issues in the ecosystem. We'll have a Q&A for that after his presentation as well. And thank you, Scott. Thank you, David.
Absolutely.
And we'll see you soon on the Ethernet. Bye.
Somewhere.